Hello everyone, I'm Ryan Shelhoum, a PhD student at Frere Mansouri University from Algeria. I'm here today to talk about transfer learning using convolutional neural network architecture for brain tumor classification from MRI images. First, I would like to tell you why we are interested in automatic brain tumor classification. Second, I will describe the methods. Then I will show you the experiments and the results. And finally, I will give you a brief conclusion. Brain tumor diagnosis is very important to develop an effective plan of treatment. The automation of the classification procedure, in particular brain MR images classification, helps radiologists in their diagnosis and reduce enormously their interventions. The first automatic classification methods are the machine learning ones. They take a long time because they need pre-processing and handcrafted feature by experts. The classification accuracy depends on the extracted features, which depends on the expert's competences. To avoid the handcrafted feature extraction, deep learning methods using deep neural networks to classify images in self-learning without the need of handcrafted feature extractions are involved. Convolutional neural networks are one of the most useful deep learning methods that have been used to solve complex problems in various applications, such as detection, localization, segmentation, classification, and they have also yielded good results in medical image application. CNNs have achieved good results in medical image application due to the growth of available public labeled medical dataset, also the increase of powerful graphics processing GPU, the rise of accuracy to solve complicated application over time, and the appearance of numerous techniques to learn features. According to the statistics that we made from Google Scholar, the number of publications that use CNNs in the field of medical imaging is increased since 2014. CNNs are widely used to classify brain tumors. According to the statistics that we made from Google Scholar, the number of publications that use CNNs in the field of brain tumor is increased since 2014. However, applying CNNs to classify brain tumors MR images have some problems. First, CNS training becomes more complicated and can lead to overfitting because of the sample size of medical data sets. Also, the training time is too long because of the large size of medical images, and the choice of epochs number is very important to minimize the consuming times and rise up the classification accuracy. So, how to increase classification accuracy, speed training time, and avoid overfitting using small number of training data sets. And what is the impact of epochs number to minimize the consuming time? In our work, we propose an automatic classification system for three types of brain tumor: glioma, meningioma, and pituitary tumor. We use the brain CE-MRI dataset from Figshare to classify abnormal brain MR images. Based on this dataset, we adopt deep transfer learning for feature extraction from brain MR images using 9 deep CNNs. We pass to describe our methods, starting by the pre-trained CNNs architectures for brain image for image classifications. CNNs architectures have been designed to learn spatial hierarchies of features by building multiple blocks, convolution layers with a set of filters, pooling layers, and fully connected layers. Here is a comparison between different CNS architectures for image analysis. As shown in the table, the classification error is decreased from 15% in AlexNet to 2% in squeeze and excitation networks. Also, the number of layers is increased from 8 in AlexNet to 152 in squeeze and excitation networks. Now we pass to present the transfer learning settings. Transfer learning used the gained knowledge that solved one problem and applied them to solve different related problems by using trained model to learn different sets of data. As shown in the figure, the CNNs used to classify different objects can be adapted to classify three types of brain tumor. Here, all these architectures are trained to classify 1,000 objects. The network takes an image takes an image as an input and produce the object label in the image as an output. We focus on slice-by-slice classification of brain tumor using MRI datasets into three types of tumors. As shown in the figure, first we modified the last three layers of pre-trained networks in order to adapt them to our classification tasks. Next, we replaced the fully connected layers in the original pre-trained networks by another fully connected layers in which the output size represent the three types of tumors. And finally, we use the transfer learned and fine-tuned deep pre-trained CNNs for experiments using MRI datasets. Now we describe our experiments. First, we describe the dataset used, then the training parameters, and how we calculate the classification accuracy. We use the public brain MRI database from Figshare to train and test our networks. It contains 3,064 abnormal brain MRI images collected from 233 patients with three kinds of brain tumors. We normalize the gray MRI images in the dataset in intensity values and we convert them into RGB images. Then we resize them according to the used networks. 200 by 224 by 224 pixels in GoogleNet, VGGNet, and ResNet, 227 by 227 in AlexNet and Squeeze and Excitation networks, and 299 by 299 in the ResNet Inception v2. We divide the data sets into training and test data, where 16% of the images are used for training and 40% are used for test. The splitting of data into train and test sets is performed on slice-by-slice basis. The network are trained by stochastic gradient descents using the following parameters. The trained networks are used to classify the test images and calculate the overall accuracy as following. The figures summarize our experiments. First, we start with the pre-processing, then we adapt the training parameters and we train our networks, and finally, we calculate the classification accuracy. Now we will discuss our results. The purpose of this study is to increase the classification accuracy, speed the training time, and avoid the overfitting. So, to evaluate the classification performance, we calculate the classification accuracy and the training times. The left table represents the classification accuracy using different transfer learning architecture for different epochs. It shows that all our pre-trained networks, except in squeeze and excitation networks, are reached up to 90% classification accuracy for three different epochs. And despite the use of transfer learning, squeeze and excitation networks has an overfitting with the epochs equal to 25 and epochs equal to 50, and have and achieved an acceptable results with epochs equal to 90. Also, the majority of the pre-trained networks record well with epochs equal to 50 and epochs equal to 25. Even though the fewer layers of AlexNet, VGG16 and VGG19 perform more than the deeper architectures such as ResNet Inception v2, and Squeeze and Excitation networks for the three chosen epochs. We observed also that with an epoch of 50, AlexNet and VGG19 achieved the same accuracy. However, VGG19 consumed a long time compared to AlexNet. Another characteristic observed during the experiment is the impact of epochs number on the classification accuracy. The right table represents the training times in minutes using different transfer learning architecture for different epochs. The training time is increasing gradually with incremental epochs number, which means that we can consume less time using less epochs. However, the classification accuracy is neither influenced by the epochs number nor the deep architectures. The table shows a classification of three samples instances using the 9 pre-trained architecture. We find that all the pre-trained architecture pertain to the class of glioma and meningioma, and all of them excepting ResNet Inception v2 pertain to the class of pituitary. This confirms that the deeper architectures don't result good with small data sets. Here we provide a broad comparison based on classification accuracy with the existing methods on the same MRI data sets. As shown, our proposed methods using the pre-trained VGG16 achieved the best classification accuracy, 98.71%. Well, that brings me to the end of the presentation, so we recap. We propose an automatic system for three kinds of brain tumor classification using MRI datasets from Figshare. The system helps radiologists to solve brain tumor classification problem and develop an effective treatment. We applied the concept of deep transfer learning using 9 pre-trained architectures for brain MRI images classification trained for 3 epochs. Our system outperforms the classification accuracy compared to related works. We reported the overall classification accuracy on the 9 pre-trained architectures based on training time and epochs number. Our system shows good performance with a small number of training samples and small epochs number, which allows to reduce consuming times. The architectures which have fewer layers perform more than the deeper architectures. For future work, we will apply the system to classify medical images from different modalities such as X-ray, PET, and CT for other body organs, and we will address the effect of epochs number to the classification performance. Thanks for your attention, and I will be very excited to answer all your questions.